Hello everyone, welcome to our AI project 2. Okay, to achieve a better performance in this contest, we apply two techniques, including approximate Q-learning and Monte Carlo tree search. By comparing these two strategies, we finally choose the approximate Q-learning as our final technique. In Monte Carlo tree search, we focus on the feature selections for evaluation during simulation processes. These are the features used in Monte Carlo tree search. And let's talk about the challenges and the improvements in Monte Carlo tree search. Since we have been given only 1 second for each simulation, it is infeasible for the agent to reach the winning status. In order to fix that issue, we decided to use the evaluation function to calculate the score of the current status. We set limit depths and evaluate the final status. And then we found that the agent is always try to run away from the opponents, even they are far away. Then we are going to set a warning distance, which is the maze distance is less or equal than 5, to let the agent know that they will be considered as a threat. And the third one is the agents don't eat a single dot. And our improvements is we set an extra feature, the dots eat has been eaten with a high value. The last one is the agents become a bit greedy and sometimes get trapped in the dead end. And our improvements is we force the agent to go back when it has eaten certain amount of dots.
For the approximate learning approach, we use the normal approach and focus on the feature selection and the weight training. We choose 8 main features to train our model, and the features are shown on the slide. The first challenge is that it's hard to find a good reward function for the Q-learning. We need more features and skill to build a better reward function. Our agent is also easy to get stuck into some deck and path. What's more, our agent usually finds the shortest path to get home. However, if there is an enemy on that path, we might want our agent to detour. During our test, we found that most of our competitors just use one agent to attack and one agent to defense. If we have 2 agents to attack, we might have more chance to eat more food. The strength of our solution is that we use 2 attackers to do offensive, which can break the enemy defense easily and has more opportunity to get into the middle of the enemy area. The other strength is that our attacker is more conservative. When they find get enough food, they will return home. The weakness of our approach is that we can't find the dead end path and usually run into the trap and get caught. Another weakness is when we go back to defense, it might be a little bit late and the enemy might already get close to the power palette. For the future possible improvements, first of all, we can add more features. We can also update the reward function. If we have a better reward function, our weight update might more easily to converge, and the weight might also close to the optimal value. The final improvement we can think of is trying to use deep Q-learning to calculate the weight and the Q value.
Here is the demonstration section. For the demos one, we want to show that 2 agents both go home and defense. For the demos 2, we want to show that 2 agents both attack on the different side. And for the demos 3, we want to show that one of our agents go back home when he got enough food. And for the demos 4, we want to show that we set one of our agents to monitor the food list and go home to defense when he finds the food list gets smaller than the previous stage. This is all information for our AI project. Thank you.